Okay, so in this video, we're going to speak about the exponential inverses. Okay, so in the name of God, the most gracious, the most merciful. So for exponential graphs, we know that, for example, f of x is equal to a to the power x. Okay, let's say y is equal to a to the power x. Now the inverse, wherever you just switch the x and the y around. So then you're gonna have x is equal to a over y. So that's the original graph. Then for the inverse, you say x equal to a to the power y. Then my understanding is that, or how I understand this is that we have to write this of y is equal to something. So you see that y here is an exponent. So the exponent becomes the answer. So y is equal to. Exponent becomes the answer. Exponent becomes the answer. So y is equal to. Then you go log. A remains the base. This is the basis. So base remains the base. So we have exponent becomes the answer, base remains the base, so it's log base to the a times x. And then you just put that x there. And that's how we go. And this is basically the inverse of f of x. The inverse of f of x is log base a times x. Okay? So this graph, so let's say, for example, in this graph, right? So remember, if a is more than 1, we have an increasing graph, an increasing function. So our original graph will look like this, right? And let's say that is our axis that we're going to reflect our graph. That's the y equal to x axis. The inverse of that graph will basically look like this. So and then so it's so, and then you flip it around and it's most likely to look like that. Okay, not too accurate, but let's say like that. Okay, so it's most likely to look like that. Okay, another point I actually want to make about these graphs is that there are certain properties we have to take into account. Now the first property is the asymptote, right? Now the asymptote, we have I'm gonna write the asymptote of the original and the asymptote of the inverse. Now if you look at this of the asymptote of the original graph over here, the asymptote here, because that asymptote cuts the y-axis, is called y equal to 0. Okay, and let's say, for example, here was plus 2, then the asymptote will be y equal to 2. Okay, because the horizontal asymptote we know is the q value. Okay, very important, but in this case it's like plus 0, so therefore the horizontal asymptote is y is equal to 0. Now in the inverse, your asymptote is basically like switched to the side over here, and therefore this asymptote of the inverse cuts the x-axis, therefore it's x equal to 0. Okay, so x equal to 0 is the asymptote of the inverse, but y equal to 0 is the asymptote of the original graph. Okay, and then I also want to mention about domain and range. So remember that for the original graph, the domain of the original graph is all the x values on the graph. Okay, and that's x is the element of real numbers. Okay, because the graph, as you can see, it goes right till the end, and it goes, and you can see that there will always be x values for this original graph. Okay, however, and then the domain of the range of the original graph. The range of the original graph, if you look at the y-axis, the graph only lies above the zero mark on the y-axis. So therefore, the range of the original graph is y is more than or equal to, y is more than 0. Y can't be equal to 0 because y equal to 0 is the asymptote and the graph does not cut the asymptote. Now for the inverse, it's very simple because all that you have to understand that it's like the domain becomes the range and the range becomes the domain. So for the inverse, you're just gonna say the domain of the inverse is so the domain is all the x values. It will be x is more than 0, you see, and the range will be y is the element of real numbers. Do you see that the range of the original graph becomes the domain of the inverse? You understand? And the domain of the original graph becomes the range of the inverse. So if you look at the inverse, you can see that for the inverse only for the x values, for the domain, it goes this inverse is only possible for values of for x values after the 0. Therefore x is more than 0. And the range, you can see that this graph can exist for all possible y values going up and going down. So therefore y is the element of real numbers. So just make an important note of that. Now that's the first graph, that's the increasing graph. For the decreasing graph, you got y a is more than 0 and a is less than 1. So the graph will look like, so that's the asymptote, for example, and then the graph will look like that. And then that is your axis of symmetry, the y equal to x line, and then your inverse will basically, that's your axis of symmetry of the inverse, and your inverse will basically also look like, so you reflect it, so it will basically look like that. Okay, something like that, or something like that. Okay, so your inverse will kind of look something like that, and again we can get the asymptote. So the asymptote of the original graph is y is equal to 0. The asymptote of our inverse is x equal to 0. You understand? And we can again get the domain and the range. So the domain of the original graph, all x values can exist on the original graph. Therefore x is the element of real numbers, and the range, you see that there is 0. The original graph lies above the 0 mark for all the y values. So only the y values above 0 lie on this original graph, so y is more than 0. Then for the inverse, the domain is all the x values for the inverse, the inverse lies only after the 0 mark for all the x values. So therefore x is more than 0 and the range is y as an element of real numbers. You can see that the domain of the original graph becomes the range of the inverse, and the range of the original graph becomes the domain of the inverse. Obviously just changing the y to x and the x to the y. That's just what we can observe as well. And I think that's it for this. That's just like a basic introduction to exponential inverses. Oh yes, before I go, I just have to mention that sometimes in the exams they give you this log graph. Then you have to go from log back to the original. So all that you do is that you say, to go back to the original, just tell yourself a remains the base, right? And that x is going to be my exponent. So then just keep the y and say y is equal to a to the power x, basically. And that's how I remember to go from the inverse back to the original. And then from the original to the inverse, you switch the x and the y's, and then the exponent becomes the answer. The base remains the base. So y is equal to log base a times x. And that's it for exponential inverses. Peace.